traps, but I want you to understand what it is and not do this. And if I use this enough, I think you'll finally, everyone will be clear that this is that represents the inverse function. So we can't look at this right here as y equals 1 over sine x. Now I think I did hear it.
You apply sine to both sides.
Okay, so we are applying sine to both sides of the equation. We're taking sine on both sides. Now, why do that? What does that do? Remember, we're trying to find y prime, right? We can do sine on both sides. On the right-hand side, what happens when you put sine and arcsine together? They cancel out. I mean, that's because they're inverse functions. One of them undoes the other one. So whatever happens, x goes into here. Whatever happens, this one sends it back to x. So this right side just becomes x, like that. And now at this point, we can try, and I don't know, I was just following your direction there. What now? That was a legal move. We were allowed to do that. How does that help us, though?
It gets rid of the inverse.
Yeah, so we don't have the inverse anymore. We have a sine there now. And we actually do know the derivative of sine, right?
With respect to y.
Yeah, so why don't we use implicit differentiation now? Take the derivative on both sides of the equation with respect to x. So I'm going to do it this way. I'm going to take the derivative with respect to x on the left side and the derivative with respect to x on the right side. Jeremiah? Jeremiah, how's it going? Jeremiah, I have to take two derivatives here. Okay? I'll give you the right side first. So what's the derivative of x with respect to x? It's just 1, right? So the right side is just 1. Okay? Do you want to keep going?
Is the left side like cosine dy dx?
Okay, close. Yes, yes. You just forgot to say y. So the derivative of sine of y is cosine of y. But the chain rule says now you have to take derivative of the argument of this, which would be dy dx. This is implicit differentiation from Cal 1. Does that ring a bell? And now we have dy dx, which really is y prime, isn't it? This is y prime. And that's what we wanted to know. So let's isolate this. Let's get this by itself. So I'm going to go dy dx equals 1 over cosine y. Divide both sides by cosine y, right? That it? So it seems like the answer should just be secant y, right? 1 over cosine y is secant y. But that's not what you're going to find on your formula sheet. What's that? Oh, I thought I heard something. Did I hear something? No? That's not what you're going to find. And the reason you're not going to find this is because this answer, look, when we take something like x squared, ask you to take the derivative, what's your answer? 2x, right? Your function started with x as the variable, right? And your answer had x's in it. Here, we're starting with y as a function of x, and our answer has y in it. We need to somehow replace the y with x. Get the y's to have x's instead. You all understand what I'm saying? So this is where we're going to use the reference triangle. All right? You all understand that we've gotten to a point where we have an answer. We have y prime, but the answer has y in it instead of x. So now what I'm going to do is I'm going to come back to this point right here. Right there. See that? That's when we took sine on both sides. I'm going to take a look at that equation, and I'm going to draw you a triangle. And I want you to take a look at this triangle and tell me if you agree with this. It's a right triangle. Call this angle y. Okay, so angle y is the angle inside of sine. Sine is which side over which side on a right triangle?
Opposite over hypotenuse.
Opposite over hypotenuse?
Yeah.
So if I call that x and call that 1, then doesn't this triangle represent that equation? Right? Sine is opposite over hypotenuse. So that picture is a perfect representation, a visual representation of that relationship that we have. What is it that we're interested in knowing? What secant of y is, right? Secant, by definition, is the reciprocal of cosine. Can you tell me what cosine of this angle is? So cosine is always adjacent over hypotenuse, right? So we don't want adjacent over hypotenuse, we want hypotenuse over adjacent, because that's secant is hypotenuse over adjacent. So do you know the adjacent side to that right triangle? Can you find it? Yeah, you have two sides of a right triangle. So we know that this side plus this side is this side. Right? So let's call this one A for adjacent. Then we know that a squared plus x squared is 1 squared. And that means that a squared equals 1 minus x squared. I'm trying to solve for a. And that means a is equal to plus or minus the square root of 1 minus x squared.
Oh, right.
It's plus or minus because of the fact that we took the square root on both sides. However, we're going to use the positive because it's the length of the side of a triangle, right?
Sine can't be on the negative side of the unit circle, right?
That's right. Yeah. Yes or no here? Can you all click yes or no on this, please? So, I'm looking at y'all and I'm not quite sure what to gather here. All right. All right, so that means that a is this. We'll take the positive, 1 minus x squared. There we go, square root of 1 minus x squared. So secant of y would be the hypotenuse over the adjacent, so we get our final result, which is this. There we go.
Is it also reasonable to say that we could have just plugged in that for cosine y?
Yes. Yep. Yeah, if you didn't write this down, then you go 1 over cosine y, go figure out what cosine y is, and plug it in. Same thing.
Same deal.
Yep. All right, so you see what we did to derive the formula for the derivative of arcsine of x. To figure out the derivative of this, we took sine on both sides. Once we did that, we did implicit differentiation, solved for dy dx, took a look at this, created a reference triangle, plugged things in, we had a formula, right? Now you can imagine you could do this for arc cosine too, right? So if I change this to arc cosine, then what would be the difference in this?
You just do opposite over adjacent instead. Just do take the
Oh, here, yes, this will be different, right? But the first step would be to take cosine on both sides, right? So let's work through this one a little faster. So here, find y prime, so we just do cosine y. Now, let me just say a little something about this, because technically we have to be kind of careful. I know that we're saying that we are applying cosine to both sides of the equation, right? I know that that's the terminology I've heard before, but that's actually not what we're doing. We're using a property of one-to-one functions. And so let me just to be clear on this. Okay, if a function f is, I'm going to do 1 dash 1. Okay, so that means 1-to-1. If a function is f is 1-to-1, then if x equals y, f of x equals f of y. Maybe I should say not if up here, just say given. Given f is 1-to-1. Yeah, that's too many then and ifs. Given that you have a function that's 1-to-1, then if x equals y, you're guaranteed that f of x equals f of y. Right? And this actually works in both directions. So does anyone know what we use when this implication works in both directions? Meaning, if x equals y, that forces this to happen, or if these two are equal, it forces that to happen.
Continuity or limits?
No, it's, let me write it. Maybe you've seen it. X equals y, IFF, if and only if. Have y'all ever seen that before?
Long time ago.
Okay. So what this means is that if x equals y, then that has to be true. And if this is true, then that has to be true. So it goes both ways. So this implication goes in both directions. So if you're one-to-one, you actually have a stronger condition than this. You have this condition. So when we're sitting here at this step right here, and we say, hey, look, we've got equality between two things. That's like saying that x equals y. We have left side equals right side. Left side equals right side. Because it's one-to-one, composing the left side with the function f and composing the right side with the function f, you maintain equality. So it's not like you're actually taking cosine on both sides, even though that's what we like to say. You're just using the one-to-one property is what you're doing. But it looks like we're taking it on both sides. And you'll hear me say it that way. I'm just trying to clarify. It's not like multiplying both sides of an equation by 2. That you're doing something to both sides. We can only do this if we have a one-to-one function. And cosine is one-to-one on its restricted domain. All right, let's continue. Sorry, I went off topic there. Cosine y, cosine y equals what? X. And then we differentiate implicitly. So Jordan, where's Jordan? Jordan, what happens when I differentiate the left side with respect to x? Okay, so the right side becomes 1. So if I take derivative with respect to x over here, derivative with respect to x over here, you said the right side becomes 1. What about my left side?
Negative sine y.
1, and then we get negative sine y. And then you want to use the y prime instead of dy dx? That's fine. I like that. I like that too. I mean, that's what I would prefer, but okay. And then now we just do what?
Divide.
Yep, divide through, solve for the y prime. Now, my reference triangle, is it the same triangle we just drew? Yes.
I have a question.
Yep.
If you get cosine y equals
Where did I get what?
on the third part,
Here?
cosine y, yeah.
Okay, cosine of arc cosine of x, these kill each other off and just spits out x. Because you're composing a function with its own inverse. So they wipe each other out. Okay, what about our reference triangle? What does our triangle look like here? We have an angle y, we have a right triangle. What sides can I label?
Opposite over, no, it's adjacent over hypotenuse.
Yeah, so this time it's cosine of y, right? Cosine is adjacent, so x over 1. X over 1 is x. So that means that this equation is represented by that triangle. Then can we solve for this side? Yeah. Same technique we used earlier. I'm not going to go through the work. And so we have this. Right? So we had to solve for that side. Yeah, so the answer to this is 1 over negative sine of y. Sine of y by definition is this over this, right? So we get, I'll put the negative on top, negative 1 over square root of 1 minus x squared. So very similar to the derivative of arcsine, right? What's the difference between the derivative of arc cosine and arcsine then? Just a negative, right? And then what about arctangent? We're not going to do arctangent. But what about arctangent? Same process, right? Take tangent on both sides, implicit differentiation, solve for y prime, reference triangle, plug in, we should get a formula. So that means that, was that we good? I thought I heard something. No? Yes.
Just to clarify, on your reference triangles, you're using SOHCAHTOA to create those reference triangles, right?
I'm using this equation, and then what is this telling me? Like cosine of an angle equals adjacent over hypotenuse, right? Cosine is adjacent over hypotenuse. That is what's dictating how I draw this. And yes, then I'm using the SOHCAHTOA. All right, so in theory now, we have 6 trig functions: sine, cosine, tangent, secant, cosecant, cotangent. All 6 of those trig functions have derivatives, right? We also have 6 inverse trig functions. arcsine, arccosine, arctangent, arcsecant, arccosecant, arccotangent. 6 inverse trig functions. And they all have derivatives. I've shown you the derivatives of 2 of them. The rest of them are on your formula sheets, all right? I'm not going to go through the proofs of those. So let's see how we might actually use this now for something. So I'm just going to make one up. If f of x equals arcsine of let's go x squared plus e to the x, find f prime of x. So what we've done is we have now added another group of functions that we can take derivatives of. So all the rules that we have in Cal 1, product rule, quotient rule, chain rule, they're all still in play, all right? And we want to be able to take the derivative of this function. So what do we have going on here? Arcsine, how would you say this? Arcsine of, right? Arcsine of x squared plus e to the x. When you use that word of, that means you're doing composition. And to take derivative of something with composition means you have to use your chain rule, right? So the derivative of this should be, let's see, what is the derivative of arcsine of this thing right here? So if that were just x, what would the answer be? If this was just arcsine of x, what would our answer be? Be 1 over the square root of 1 minus, and it would be x squared, right, if that were just x? But it's not x squared, it's everything in there, right? So we have to have x squared plus e to the x squared.
It's a formula, isn't it?
What is?
That's like u over.
Yep.
square root of
Yeah, so what we've come up with here is that if y equals arcsine of x, what I just proved, or what we just proved together, is that the derivative of this would be 1 over the square root of 1 minus x squared. That is our new formula. And there's 6 of these. There's one for arcsine, arccosine, arctangent, right? And what we've done is we're using that formula with the chain rule, and we're saying, like, if this is u, anything, then the formula becomes u squared, right? Is that what you're referring to? Okay, so now we can use it with chain rule just like we did with all the other ones. Am I done? No, what do I still need?
You take the derivative.
I need to actually take the derivative of the argument, of the thing inside of here. Now, what's the derivative of that argument? 2x plus, so derivative e to the x is itself. And is that correct? Just like that? I've either got to move this up here, or I've got to put this in parentheses, one or the other. I can't just leave it hanging out there like that.
Question.
Yes.
What do you multiply with 2x plus 8x? Yeah.
Why did I? Chain rule. So let me do this. Let me ask you a different question. Let's keep this up here, but let me ask you this. What if I gave you y equals sine of x squared plus e to the x? And ask you for y prime. So not arcsine, but just sine. Right? Then you would have to use a chain rule for this. You would say derivative of sine of something is cosine, right? Cosine of x squared plus e to the x. But then the chain rule would say that you now have to take multiply that times the derivative of what's in here, right? Which would be 2x plus e to the x. We're doing the exact same thing, except that derivative of sine here being cosine is different because we're doing arcsine. So derivative of arcsine of something is 1 over the square root of 1 minus that thing squared, right? And then this is the end of the chain rule.
I see.
Does that clarify it?
Yeah.
Okay. We all good with that? Okay. Let's go back to these notes here. Yeah. Let's do that one. That one looks fun. Okay, why don't you take a minute to see if you can get the derivative of this one. So basically this is you bringing in what you know about Cal 1. I haven't given you the formula for that one, have I? No. All right, so it's in your formula sheet, but since you may not have that with you, I'll put it right here for you. If y is equal to arctangent of x, the derivative of that is 1 over 1 plus x squared. Okay, put like several stars next to that one. This is going to come up a lot. All right? What did I say? This is going to what? What did I say? This is going to come up a lot, okay? The derivative of arctangent of x is 1 over 1 plus x squared. I'm only going to give you like maybe another minute to try and get that derivative.
Oh, super.
When you have an answer, click number 1 or A on your thing. When you have an answer. You don't have to simplify the answer. Just take the derivative. Just get like a raw derivative out there. You don't need to clean things up. I just want to make sure you understand how to apply the chain rule to this. Yes.
So now I'm taking the first derivative here, or the derivative here,
Mm-hmm.
and then the derivative of the inside is going to be that same deal.
Mm-hmm.
But I mean, there's nothing else to put in for x, so it's just x squared then.
Where's that? The derivative of the natural log
Is 1 over x.
is 1 over the argument. So it should be 1 over arc tan x, right?
Oh, yeah, yeah.
And then the next piece will be the 1 over 1 plus x squared.
I
Yeah.
got you. Thank you.
And I think you're missing a 1/2 on the, like this whole thing. No, 1/2 here, but it's, oh, is that a square root right there?
Yeah.
Okay, I didn't see the square root. Yep. All right, so we have 7 answers. I want to see when we got everyone here.
So the tangent and the linear is both one function, right?
It's a function inside of a function, yes. So that's composition. So you got multiple pieces to the chain on this one. All right, we still only have 7 answers, but I'm going to go ahead and put the answer up here. That's not cleaned up or anything. It's just I'm just leaving it all kind of ripped apart so you can still see where everything came from.
Is it like like the same like this. I'm not sure. Gonna be half in the root.
Yeah, it's a negative 1/2.
Yeah.
And
multiply
this part right here, there's something off. Because first thing you have to do is you have to take derivative of the square root of that thing, right?
Yeah.
So that's this piece, which is, you've got that, right? But then you have to go inside, take derivative of the natural log of arctangent. What is the derivative of natural log of something?
It's one.
1 over the something, whatever that something was, right? So derivative of natural log of this should be 1 over it, right? And then times the derivative of what's in here, which is 1 over 1 plus x squared, because I gave you the formula.
Yeah. So this one, the power and the channels too, right?
There's no power, well, no, because, oh yes, power rule in the beginning, yes. The 1/2, yes, you can look at it that way. Because you were looking at it like this, natural log of arctangent of x, all of that to the 1/2 power. That's the way you were looking at it, right? And then you say, okay, 1/2 comes out, subtract 1, right? That's the way you were doing it?
So it's like the derivative of the outside multiplied with the derivative of the inside, and then the derivative of the tangent and
Are you thinking product?
yeah,
There's no product though. This is not a product.
it's one thing.
It's natural log of.
Yeah.
Now, had that been natural log of x times arctangent x, then you would have had to have done product rule. Because it'd be natural log of x times arctangent of x. But there's no x here. It's natural log of arctangent of x.
Isn't there a rule with like logarithms and natural logs that you can just pull the exponent to the front right away?
Yes. Are you saying for the root?
Yes.
The root would have had to have been right here. So it would have had to have been written this way. Like this. Had this been the original problem, right? Then we could have rewritten it like this. Where the 1/2 is acting just on this. Then the 1/2 could come out. Okay? The problem here is that right there, this right here, this half is acting on the entire expression, including the natural log. So you can't pull the power. Does that make sense? We have this property right here. This is the one you're referring to. When you see this, that n is only acting on that x, not on the whole expression. Yeah. Okay, I think that's probably enough time on that one. We've only got what? Yeah, we go till what, 12:40? Look, we're just trying to get your brains warmed up here today, all right? Just trying to get you going again. Hopefully you had a good summer and you were able to decompress a little bit. Okay, let's try this one. The point that I'm trying to make with these two examples is that all we've done is introduced 6 new formulas. But everything we did in Cal 1 is still in play. All the different rules. We just now have more things to worry about, all right? So on this one, we're trying to find dy dx. The problem is you can't solve for y here. So to do this one, you have to do implicit differentiation. Just take derivative on both sides with respect to x. So I'm going to walk us through this one. The derivative with respect to x of the left side. And then the derivative with respect to x of the right side. All right, let's start with the right side because I think it's easier. Let me see here. I'll just pull a stick here. Christian DeLuna? Yes. Okay. I just want to see how you feel about the derivative of the right side with respect to x. So derivative of that would be 0. Okay, I'm going to put it here. Plus, now what do you have to do with that x times y? So it's a product, isn't it? Isn't x times y a product? So that means you have to treat it with the product rule. And you're differentiating with respect to x. which means that the derivative of x is just 1, but the derivative of y is y prime. So if I do the product rule here, you would do like the derivative of this one times this plus the derivative of this one times this, or you can do it different orders, but okay? So try it again. What would you get there then? So take it through slower. Okay, you're going to do derivative of this one first. So 1 times y, right? So y plus, now you do derivative of this one, right? Y prime times x. Does that kind of ring a bell now? A little bit from implicit? How do y'all feel about that one? Can y'all, this right side, does this seem okay? Does this look familiar? Okay, I'm getting no no's, no negative results right now, so.
Think about face with the no dy dx thing.
Yeah, there's different notations, right? So it's, yeah.
Bob is
How about the left side? The left side's the harder one. I've saved that for, let's see, Tatum. Tatum, what is the derivative of arcsine of something? Okay, 1 over square root of 1 minus whatever's in here, which is actually xy squared, but then squared, right? That's the derivative of arcsine of something. That's the thing we've added to our arsenal today. But we're not done, right? We now have to multiply that by the derivative of what's in there. And that, Luis gets the inside piece. That's all right. That's why I asked. That's why I'm calling on you. So what do you see here? What is the operation between these two? Product. So you got to use a product rule, right? So derivative of this first one with respect to x, 1 times y squared, right? So you're going to have just y squared and then plus, now do it the other way. What's derivative of 2y, careful, 2y, y prime, good. And then times x, because you've got to finish off the product rule, right? That make sense? So derivative of arcsine of something is this piece. Chain rule says take derivative of what's in there, but then you have to go back and do your implicit differentiation. Okay, yes or no on this? Just give me some no's if you're having any trouble. That's okay, that's what I need to see. But if you're a no, you need to ask me, you need to tell me what I need to clarify. Yes?
So for the inside where you have, you do the product rule to get that, and then the chain rule?
Are you asking how I got this?
Yeah.
So I'm looking at this and I'm saying, what's the outer function? The outermost thing is the arcsine, right? The derivative of arcsine of something is 1 over the square root of 1 plus the argument, whatever's in here, squared. That's like a general formula now. But then once we've done the derivative of that, we go in here and we say we have a product. So we have to do derivative of this implicitly with respect to x using the product rule. So derivative of x is 1 times y squared, which is y squared. Plus derivative of y squared is 2y y prime, and then times x. And that finishes off our product rule. Then we're done on the left side. And then the right side, I think everyone was okay with. That better?
Yeah.
Yes?
No, what's the formula for the product rule?
He's talking about your
Derivative of the first one.
Which, the derivative of the product rule? I mean, sorry, the formula for it?
For the product rule, yeah, like the way.
Is there a reason you're asking me?
I just don't remember.
That you need to remember it. I'm not going to tell you it. Yeah. I mean, you need to know that. You need to walk in here, everyone needs to know the product rule. Yeah. So you need to go review. I mean, seriously, product rule, quotient rule, power, all those have to be like 2 plus 2 to you right now. Yep. Okay. I don't mean that to just you. I mean that to everyone in here. Like, you learn the product rule in Cal 1, to apply it in Cal 2. If you walk it in here and you don't remember the product rule, go review. All right, last one. Yeah, don't take that the wrong way, Chris. I just want everyone to understand this is not going to be there's no more baby steps. Baby steps are in Cal 1. Now it's time for, you got to bring it. You got to bring it. You want to be the engineer, you got to be able to compete. And you can't be in Cal 2 not knowing what cosine of pi over 2 is. You can't be in Cal 2 with knowing these basic things. Can't be there anymore. All right? Okay, here we go. A rocket, I'm trying to convince you why this might be useful to us. Here we go. A rocket is fired straight up with the speed of 1,000 miles, or at a speed of 1,000 miles per hour. So this thing is taken off. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? And what is that in degrees per second? Does this problem look like something you may have seen in Cal 1? Okay, this is a related rates problem. Let me see, I think I might, no, I don't have a picture. Good, fine, don't need it. So we're going to draw a picture. And with related rate problems, again, depending on how you learn this, everyone's going to have kind of a different approach to it. So I'm not here to try and reteach related rates, but I'll approach it the way that I approached it in my class, which is I always had my students draw two pictures. A general picture, and that's where everything is in motion, and then I have them draw a picture of what's happening at the instant in question. So the general idea here is that we have a rocket that's going straight up. So I'm going to draw the ground. I'm going to draw a rocket that's going straight up, right? And let's just say that that rocket is that point right there. I could draw a little rocket, but I'm just going to draw that point. So my rocket's moving vertically, right? I have an observer who is standing at some other point, and they are watching that rocket with their binoculars, like this, right? Is there anything on that picture that I can fix that's never going to change throughout the problem?
The base.
The observer is a mile away from the launch point. That's not changing, right? So I can say that this right here is always 1. I'm just going to put 1 for 1 mile. Other than that, this red dot is moving, right? And the distance between the blue one and that one is also changing. And the angle of inclination, which is this angle right here, is changing. So I'm going to label those. I'm going to call this theta, and I'm going to call this y. And I'm only calling it y because it's vertical, and usually the y coordinate's vertical, right? So that okay? That's my general picture. Now, the instant that we're talking about is actually when the rocket is 3 miles high. So at exactly the moment that my rocket is 3 miles high and my observer is still 1 mile away, right? 1 mile from here to here. My angle should be known at this point, shouldn't it? Can anyone tell me what that angle is without a calculator? Just give it to me, like, what would you type into your calculator to get that angle right now? Arctangent of 3 is that angle. Because what's tangent of this angle? Opposite over adjacent, right? So arctangent should give you back the angle for that. What I'm getting at is here things are changing, here everything's fixed, right? Okay, so that's what I do in my classes. Then the next thing, see if anyone remembers the next thing. Once you have kind of a picture and an idea of what's going on, you can write out things like do you know how fast y is changing? So you're given that y changes with respect to time. What's that rate? 1,000 miles per hour. Right? What do you want to know? So in my classes, I usually say draw a general picture, an instant in time. Write down what you're given and write down what you want. So what do we want? We want, not theta, the rate at which theta is changing, right? Because it says, at the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? We want to know d theta dt at exactly the moment that y is 3. Okay, I know this is kind of sloppy, but we have a picture, everything's moving, instant in time. We are given how fast y is changing. We want to know how fast theta is changing with respect to time at exactly the moment that the rocket's 3 miles high. Does that look like something from Cal 1, something that you may have done, or the way it was kind of presented? Okay? So what's the next step? You have all this information. What's the next thing you need to move on with this problem? An equation. That's the key. You need an equation that somehow connects what to what?
The original to the change that they.
Yeah, your given variable over to your variable you want. Any equation that you can come up with that connects y and theta together off of this picture. Not this picture, this picture. So what equation connects y and theta together? That's Pythagorean, but that would be using this side. I want the theta and the y to be connected.
Tangent.
Yeah, how about tangent?
Theta.
Do we all know tangent? Theta is what, according to this picture? Tangent theta, so I'm coming up with an equation now. Tangent theta is y over 1, right? Just y? Just off this picture. Now, what do you do once you have an equation? Take the derivative with respect to time, right? Because we know dy dt. We want d theta dt. We want to know how these variables are changing with respect to time. So we differentiate with respect to time. Yes? Okay. So let's work through this. I'm out of time. Damn it. I'm out of time, right? 12:40? Okay. Let me do something real quick. We're going to have to pick this up later. Okay. Everyone hit number 1 on their thing. Everyone hit number 1. Hold on.
The new guys.
Well, that's why I'm doing this. Everyone hit number 1. Next class. What next class? I don't. Oh. Oh. Okay. All right. Yeah. So never mind about that. I thought that maybe that was Johan. No. Johan's not here. Is Johan here? All right, so we have to stop in the middle of this problem, right? We have to stop. But at this point, you would take the derivative. What we're going to do when we come back next time is I'm going to do it this way. I'm going to finish it. And I'm going to show you a slightly different way, and you'll see the difference between the two and why the derivative of arctangent actually makes this problem easier than if we don't use it. So stand by. We'll do that next class. This sheet right here, I didn't have time for it. We're going to turn this in next class. If you cannot find people, that's okay. Just still turn it in because I want to be able to, look at it. All right? Okay. Clickers, yeah, you know what? Just leave the clickers on the desks and I'll come pick them up.